Welcome to Infinite Series. This is a long section, so I'm just going to jump right in. A sequence, we talked about last time, that's a list of numbers. A series is a sum of numbers. So this is a summation sign. It says start at 1, go to infinity, add up a1 plus a2 plus a3, etc., etc. What we want to talk about today is what it means for those numbers to add up. So in my first example here, I've got a sum of numbers that seem to add up to 0 because every time I get a 1, I get a negative 1 to counter it. It turns out that those numbers actually don't add up to 0. They don't add up at all. We say that infinite series diverges. The second example, we've got 3/10 plus 3 over 100 plus 3 over 1,000. We'll see later today that that does converge. That means the terms add up to a third. So what does it mean to add up? We've got some definitions here that you do need to know. The nth partial sum of a series is the sum of the first n terms. A series converges if the limit of the sequence of partial sums exists and is S. So we say the series converges to S. Otherwise, the series diverges. Now, to make this more concrete, I've got an example for you. Here's our infinite series, 3 over 10 to the n. I've written out the first 3 partial sums. S1 is just the first term, that's 3/10, 0.3. S2 is A1 plus A2, that's the sum of the first 2 terms, that's 0.33. S3, sum of the first 3 terms. Those S's form a sequence, S1, S2, S3. If the limit of that sequence exists, we say the series converges. It's very tricky, I know, but this is why we talked about sequences in the last section. And yes, the limit of that sequence does exist. It's 1/3. And we'll see an easy way to show that later on today. So don't worry, we won't have to be writing out all the partial sums in order to find sums of series today. All right, properties, I'm going to let you read that on your own in the interest of time. Go through, read it, and there are 2 examples there. What I'm interested in today is geometric series and telescoping series. A geometric series has this form. It's a constant times some number to the nth power. And so let's just go through these examples here and decide which ones are geometric. So this first one, let's see, does it look like a times r to the n? No, not yet, but it will in a second. Let me rewrite it. N goes from 0 to infinity. That negative is not being raised to the nth power, so I'm going to pull that out and write 5 over 6 to the n. Okay, those are equivalent. Now it's geometric. A is -1, r is 5 over 6. So that is a geometric series. And we need to identify A and R in order to find the sum, and that's why we're going through that here. Next one, no, factorials aren't allowed. Next one, yes, this is geometric, but in order to determine A and R, we need to rewrite it. N equals 0 to infinity. Now the negative is being raised to the n, so this is the same as -5 over 6 all to the n. Take a careful look at the difference between the first one and the third one. They're very different, even though they look similar. Here, A is 1. There's an imaginary 1 sitting out there. And R is -5 over 6. So in the first example, A was negative, R was positive. In this example, A is positive, R is negative. Okay, next one, no. Nothing's being raised to the nth power there, not geometric. This one is geometric, but we need to rewrite it in order to determine A and R. 0 to infinity. 3 is 3, so that just sits there. And then we have 1 over 2 to the n. And in this box here, I explain that 1 over 2 to the n is the same as 1/2 to the n. Because in order to write it in this form of a geometric series, you can't have the r in the denominator. It has to be a times r to the n. So in this case, our r is 1/2. So a is 3 and r is 1/2. All right, to find the sum of a geometric series, they have to start at 0. Sometimes the series won't start at 0 and you need to rewrite it. And so here's the rule. Whatever you have to do down here to start at 0, like subtract 1 or add 1, you're going to do the opposite in the formula. So let's just do a couple of examples. This first one starts at 1, and we want it to start at 0. So I need to subtract 1 from the index down here at the base. I'm subtracting 1. That means everywhere in the formula, I add 1. So 3n plus 1 over 2 to the n plus 1 minus 1. Now I can just do some cleanup. That's n equals 0 to infinity of 3 times n plus 1. Yes, you could distribute the 3, but I'm not going to, over 2 to the n. So it's the same sum, I've just rewritten it. Okay, next one. Again, this one starts at 1. We want to start at 0. So I'm going to subtract 1 downstairs. I'm going to add 1 everywhere I see an n. So negative 1 over 3 to the 2. Be careful here. It's not 2n plus 1. It's 2 times n plus 1. So I have to distribute that 2. That's 0 to infinity of negative 1 over 3 to the 2n plus 2. And we'll actually find the sum of this geometric series on the next page. This guy is not geometric. The first one's not geometric, but you can still reindex it. All right, here's how to find the sum of a geometric series. You might have to reindex it so it starts at 0. If it looks like this, then its sum is a over 1 minus r as long as the absolute value of r is less than 1. If it's not, the series diverges. Okay? Some textbooks have a slightly different formula, not starting at 0, but in my class, you're going to have to reindex to start at 0 always and use this formula. This is the way most of the world does it. Okay, so first one, we need to reindex. N equals 0 to infinity, 3 over 10 to the n plus 1. I had to subtract 1 here, so in the formula I add 1. Now I need to make that look like a constant times something to the n. So n equals 0 to infinity of 3 over, I'm going to write 10 to the n plus 1 is 10 times 10 to the n. That's certainly true because 10 is 10 to the 1. Then I'm going to cull off the stuff that's not being raised to the nth power. That's 3/10. All right, and what's left is 1 over 10 to the n, which I'm going to write as 1/10 to the n. So now I'm good to go. A is 3/10, r is 1/10. The absolute value of r is less than 1, so this converges. And it converges to a over 1 minus r. A is 3/10, r is 1/10. Now, typically you're going to get a complex fraction when you use that formula. My suggestion is multiply top and bottom by the smallest number that will clear all your denominators. In this case, I'm going to multiply top and bottom by 10. On top, I get 3, and on the bottom, multiply this whole thing by 10, 10 minus 1, which is 9. 3 over 9 is a third. So that series converges to 1/3, meaning if I add up all the terms to infinity, I get a third. Okay, next one. It already starts at 0. Good. We don't have to reindex, but we do have to do a little bit of cleanup. We need to write this as some number times something to the n. Well, 7 has no exponent over it, so 7's our a, and then negative 1/6 is our r, because all of that is being raised to the n. So a is 7, r is negative 1/6. R can be negative. As long as the absolute value of r is less than 1, you're good to go. So s is a over 1 minus r, which is 7 over 1 plus 1/6, because it's minus a negative 1/6. Multiply by 6 over 6. That will clear your denominators. On top, you get 42. And on the bottom, you get 6 plus 1, which is 7. 42 over 7 is 6. Okay, next one. Now, this starts at 2, so I need to subtract 2 downstairs. And everywhere in the formula, I'm going to add 2. So I'll get 5 to the n plus 1 over 4. N plus 2 minus 2 is 4 to the n. All right, think of 5 to the n plus 1. Do my scrap paper over here. Is 5 times 5 to the n. So you're going to cull off the 5. This is 0 to infinity, 5. And what's left is 5 over 4 to the n. So our a is 5, and our r is 5 over 4. Now be careful, don't use the sum formula on this one. The absolute value of r is bigger than 1, so this series diverges. Okay, last geometric one. we showed on the last page that if we reindex this guy, we get this. So now my job is to write that as AR to the n. So I'm going to rewrite it like this: sum n equals 0 to infinity of -1 over, okay, I'm going to write it like this: 3 squared times 3 squared to the n. Okay, so pause the video and make sure you agree that that's the same as 3 to the 2n plus 2. That's the sum n equals 0 to infinity of, if I cull off the part that isn't being raised to the n, I get -1/9, and what's left is +1 over 9 to the n, which is 1/9 to the n. So a is -1/9, sorry, and r is 1/9. Absolute value of r is less than 1, so I can use the sum formula. A over 1 minus r, -1/9 over 1 minus 1/9. Multiply by 9 over 9. On top, I get -1, and on the bottom, I get 9 minus 1, which is 8. -1/8 is my sum. All right, we're almost there. Telescoping series. Telescoping series are not geometric. They're telescoping, and you'll see why they're called telescoping in a moment. But if you want to find the sum of a telescoping series, what you're going to do is write out Sn. You have to include the nth term, and you're going to simplify it. All the middle terms will cancel. Then you're going to find the limit as n goes to infinity of Sn. That limit will be the sum of your series, if it exists. So this first one, I've already started us out. I've written out Sn. Sn is the sum of the first n terms. So this was A1, this was A2, this was A3. Usually writing out 3 terms is enough, and then always write out the nth term. So there's going to be a ... in there. Then see what cancels. So in this case, I've got a -ln√2 and a positive ln√2. And then this guy cancels with 2 guys up. This guy cancels with 2 guys up. You can see that every term is canceling with 2 in front of it. So this is going to cancel with the term that came before. The only 2 guys that aren't going to cancel are this first one and this one. So Sn, and that's why it's called telescoping, middle terms collapse. Sn is -ln of √1 plus ln of the square root of n plus 1. Now, that is just ln of the square root of n plus 1 because ln of 1 is 0. All right, now we take the limit, so we're up to step 2, limit as n goes to infinity of Sn. That's the limit as n goes to infinity of natural log of n plus 1. This is natural log of infinity, which is infinity, so this is infinity. Since that's not a number, the series diverges. We'll just write d with a circle around it. Series diverges. I have to get a finite number. Okay, next example, we will get a finite number. So this series doesn't look telescoping if you just write out the first few terms. In fact, there's no minuses in it at all, and so nothing collapses. However, if you do partial fractions on this, you will see that your new series looks like this. And that's for you to do at home. Verify that my partial fractions are correct and these 2 infinite series are the same. But this one actually will look telescoping. So I've started us out. I've written out A1, A2, A3. That was enough for me to see a pattern, and AN. The reason why you always want to write AN is because you need to see which of these 2 cancels. It might be the first, it might be the second. So in this case, the cancellation happens on the inside. All these inside guys cancel, and so this guy is going to cancel out. And the only 2 terms that are left are 3 and then a -3 over 2n plus 1. All right, and so the limit as n goes to infinity of Sn is 3. So 3 is the limit, and that means this series up here, my original series, converges to 3. And that is the end of this section.